Okay. Okay, back to isolation mechanisms. So this is what we were doing last time, right? So the goal is to remember we talked about microkernels. We seem to be captivated by the idea how they like elegantly design the world. Everything is a capability. If you build the system like that, everything will be much better. But really, the two reasons why people are excited about microkernels are why. What are the reasons? Who can tell me? We actually discussed them last time. Who wants to be a microkernel researcher? Well, remember why. I mean, I said two, maybe there are more. The first one, microkernels are small, 10,000 lines of code. If you look at it for a while, you can convince yourself that it's correct. It does what it expects to do. And plus, you can actually build a mathematical proof, meaning formally verify it. It became feasible. It used to take many years to verify 10,000 lines of microkernel code. Now I kind of argue it takes less than a year. Let's say 1 year. So that's kind of very cool because you have a small piece of code on top of which you can build strong isolation boundaries. And then at least you have a guarantee that if something goes wrong in those isolated compartments, like one of them crashes, the crash is limited, so it cannot escape the isolation boundary. And if the microkernel is designed carefully, it means that it cannot even affect the other subsystems by, for example, fogging by shared CPU resources or maybe shared memory. Because if your microkernel is clever enough, you have a strong guarantee that that thing is confined. That's nice. And so two reasons are like ability to reason about the small core and come up with guarantees for security of this system, and to some degree about reliability. Right, so maybe if this crashed, you can kind of restart, right? And such guarantees were nowhere around in our monolithic kernels. Like if you take a look at x86, everything is shared. There is no such thing as this isolation boundary. In x86, any process can allocate any amount of memory. It can allocate all memory immediately on was the very first system call. Now, nothing will stop it. If you take a modern hypervisors and containers, they have some kind of a patchwork kind of band-aids here, trying to implement this boundary, but they fail. So you really have to be carefully. You have to carefully design what you're building to make sure it supports isolation. So this idea of microkernels should, I'm not saying that you have to build everything as a microkernel, but just keep it in mind that when someone approaches you and they say, look, I really want something secure and reliable, think about the design principles implemented in microkernel systems. They're probably the cleanest we have today. However, as we said, okay, we don't like microkernels because they're hell slow, right? Because switching or sending an IPC, I'm drawing it as this, was always like a slow thing. So the first microkernels essentially were doomed because of that. So people didn't know how to build this fast IPC. The first line of microkernels, we know them as Mac, right? So Mac is alive. So where is Mac now? Who knows? I'm not saying that this is the very first microkernel. It's the very first kind of biggest microkernel which made a splash. So what's the fate of Mac microkernel today? It's used in production. A couple of people in this room are running it right now.
hardly used in Mac.
Correct. So Mac uses a mic. It's kind of nice to look, and I didn't look recently, so I cannot really like make very strong claims about architecture of Mac. But it runs Mac microkernel, and then it runs FreeBSD on top of Mac. And FreeBSD is like Linux-like kernel, and then it runs like userland. The problem is that they don't like implement those isolation boundaries on top of Mac, which is called, I think, a hybrid system. So it's kind of like they don't cross they don't cross address spaces. It's kind of like a microkernel sends messages across, if I understand correctly, and remember correctly. But it doesn't really provide isolation. It's just too slow. But they still build it. So we have to come back to Mac maybe towards the end of the class to just like see how stuff is used in production. So this is fun, but okay, this is gone. And the second wave of microkernels, which is like L4 line, which again, people say that we're also running it, not on Android, but on some phones, like it's used as a hypervisor. I don't know, like we should investigate this claim as well, but people were saying that it was one of the most widely deployed microkernels, which runs on almost every phone, besides maybe a few in the world. But this one, again, so Mac was like hell slow. This one is 850 cycles to do an IPC, also expensive. And that's why we're looking at this. Like hardware people started thinking about how to make those isolation boundaries less intrusive. So essentially allowing you to build systems which are not always microkernel-like, but at least they employ fine-grained isolation for security. The reason is that, and that probably, like I said, first reason is this, kind of, you can take a look at this. I mean, I forgot what I said, like, exactly. One reason is that you can take a look at the microkernel and convince yourself that it does what it's expected to do because it's small and you can actually write a formal specification of what it's supposed to do. And a second is that if you have piles of garbage sitting around, which we have after like 50 years of developing kind of trash in a shared memory model, one of the few ways to make sure that we trust those systems or kind of like semi-trust them is to run this piles of trash in isolation. So essentially, my own work takes Linux kernel and cuts out semi-automatically parts of the Linux kernel, specifically device drivers, and runs them in isolation. And it's kind of like an idea which might become practical, might not. But the idea is that you say, look, I don't want to lose, decades of engineering wisdom because people were building those device drivers. There are like tens of thousands of them. But still, they're old and no one really maintains them sometimes, or they are built in unsafe C and no one can get it right. And so they're exploitable. And one way to secure yourself is to run them in isolation, right? And the thing is how, like essentially today and maybe like Monday, our goal is to dive into those low overhead isolation mechanisms, which modern CPU architects are trying to put in their CPUs, in commodity CPUs. And my claim, spoiler, that they were kind of failing for now, but maybe they will get it, eventually we'll get it right. Okay, cool. So this is about where we stopped last time. I was trying to move this. Yeah. Look, the mouse is here, but it's not clicking. What am I doing? This. How? Any ideas how to move this thing? Exit the presentation mode like this, and then it will show up somewhere. Wow, smart. Now I have to put it somewhere here. Let's show. Good. Okay, so again, we never really talked about what would be the nice way to build those isolated systems, but because I was only explaining microkernels, and it's all good. It all runs. Seems very, very elegant. It says that I lost my Wacom pen. Really? I didn't have it today. Did I just drop it? I wanted to. Okay, it's not critical. It's still sad. Yeah, usually it's still mounted. Okay, with this one. Uh, like, remember, like when I start talking about microkernels, we always thought of them as processes which kind of run on top of a small kernel, kind of x86 style, and then send messages from one process to another. If you start thinking about it, you say, look, guys, I really have a bunch of legacy code sitting around. And really what I care about is just exposing function code. So like in this diagram, this subsystem B, we do have a function, some function. And really what we want to do is just be able to call this function across the isolation boundaries. And in a modern world, the scenario in which we want to invoke those functions are much more abundant than just like as a like you calling a file system and it runs as a process instead of being in a kernel. So this scenario started being used widely around like probably most widely deployed thing today is around web browsers and on the edge of the network. So for example, CDN providers, what is it, content delivery networks, they say, look, we will allow you to run your own code on the edge of the network, but we want to run it in isolation. And what roughly they are doing, they're saying, okay, and context switching and stuff is too expensive. What we're going to be doing is that within one process, we'll somehow carve an isolation boundary. And we'll be calling those functions fn. And if you find a bug here, or maybe it's encrusted code altogether, like maybe it's a web plugin in a browser, right? Then, you know, the bug is confined. And it's really kind of like glorified microkernel-ish, or let's say it's maybe not a microkernel because it's just literally just a function or a collection of functions. So it might be a library, like a JPEG library, which you downloaded, and who knows when it was built and how, but it's useful because it allows you to transcode a movie or something, right? Or stuff like that. And really, what's on the picture is that it doesn't go like through the kernel to invoke a rendezvous point, to jump back here. It doesn't run a separate thread here, right? It's really just one thread of execution, which kind of jumps across, but switches the isolation boundary as it goes, right? And despite the fact that I never really talked about it, the scenarios are deployed. So like, we will talk about a couple today, but you probably heard those words. One of them is called WASM, which is WebAssembly. And it's an idea that you can take C code or C++ or whatnot even Rust and compile it in such a manner that somehow it implements an isolation boundary similar to like an address space, right? And the second idea, obviously, if you want to go through the kernel, like in a microkernel, then it already takes too much time, right? Because if you doing a syscall, this is roughly like 100 cycles one way. You multiply it by 2. If you change a page table, it's roughly like whatever, 250 cycles, right? Again, multiply by 2, then the whole round trip becomes close to like 500 cycles. It's plus some checks, so it's like the minimum is 800. But we really want to make this crossing close to an overhead of a function call. Right? Then it's viable. It runs in your web browser. Maybe it's some untrusted plugin, goes back and forth. Wow. If it's a function call, then you can invoke those functions frequently. And on my diagram, I also claim that in many cases, in order to pass data around, it's easier to have a special heap. Like kind of instead of like inside here, you will have a private heap, meaning that if you invoke a malloc, malloc will return you something. Maybe malloc runs outside, maybe it runs like here. Malloc returns you something, but it sits here in a private heap. But you cannot move this object outside. And maybe you cannot move the object from a private heap here into the isolated subsystem. But often it's somewhat easier to build like a separate exchange heap. And then there are reasons for that as well, and we'll talk about it. But okay, so that's why I put like a separate heap here. Although strictly speaking, it's not always required. Questions? You didn't get what?
Exchange, like all of the elevated heaps will be there.
So yeah, so this subsystem will have a private heap. This one will have a private heap, but you cannot move the objects in them. And only the objects allocated on the special exchange heap will be like passed between the subsystems.
What's stopping the exchange?
Like in system B.
Yeah, like stop.
Meaning, I mean, first of all, I didn't get your question, but probably what you're asking is like,
Everyone shares the exchange.
right. And the question is like, what if system A passes like an object to system B, but still retains the pointer, and then maybe like overwrites part of it? Yeah. Yeah, so clearly it's not a good idea. Or I mean, it's an okay idea, but in some scenarios. And again, there's a variety of attacks. We should probably consider them one by one. But the most primitive attack is that imagine this system A creates an object in an exchange heap, then passes it to system B. System B starts doing something with this object, maybe writes, maybe there's even a pointer if the heap allows it, to another object, and maybe this system A somehow overrides this pointer and it points to nowhere now. And this guy references a pointer, gets an exception, and maybe the runtime has to cross it, right? That's a good question. Again, it's up to you as a designer to solve those problems, and you can choose a stance. You can, for example, say that only the flat, or let's say good old plain data objects, kind of like think of buffers, live on the shared heap. So there will be no semantics of a pointer from one object to another, which at least prevents this guy from this attack, right? So like, there are no pointers on this heap. Everything is like kind of just a dumb buffer. Wow. Then like it complicates the programming and stuff like that, but at least some attacks disappear. But still, as I keep saying, there might be some flavor of time of check, time of use attacks where, for example, if B checks some property of an object, A equals to 0, and makes some kind of a decision on it. And meanwhile, A overwrites 0 to 1, confuses B into some kind of a like crush, right? Because at this point, maybe B checking once that it was 0 makes some kind of a decision. Maybe it's like passes a length, how many objects they passed or something along those lines, right? Yeah, and we can talk more about it. In general, my stance on this, and the stance of some other people, which is growing today in the community, that objects on the exchange heap, they can be passed across, but at the moment of passing, they're moved. That's why I have this move word here. And this move semantics means that if subsystem A sends an object to B, it guarantees to lose access to this object, which solves a range of those attacks which Jared was asking. So A cannot change the object after it was passed to B. B can pass it back at some point, and then A gets object again. But it's easier to structure systems, and especially there is an argument that it's easier to, at some point, if B crashes, you somehow have to clean up all the state owned by B on the shared heap, right? So somehow you have to say, look, those objects, they're inside B, so let's clean them up. And there was a range of systems with different constructions. Like I mentioned Singularity, and Singularity was the first one which introduced linearity. And linearity stands for, it's a linear type system. There's this, it used to be a corner case who no one cared about in programming languages community, but it came to become a powerful concept. It's a type system which says, okay, the object can be used n number of times. A typical n which is chosen is 1. I mean, it can be a little wrong with how I say this story, but this is essentially equivalent to the single ownership. So this object on the heap has only one owner. And when you move it from one subsystem to another, since it's one owner, ownership is changed to B. And if you implement this invariant, if B process, if you somehow track ownership of objects in shared heap or exchange heap, then you can clean it up, right? That's nice. It's a nice property. Although before that, there was a range of systems like some of them developed here in Utah. You will be surprised. There was a system called, I think, Java OS, which used Java to implement all these isolation boundaries, right? And there were different, like, no, it wasn't Java OS, it was Kafka OS, which is like the word play on Java, so it was using Java. But okay, so let's for now think it's single ownership, right? And second, this powerful idea of using one thread which goes across. And there was an interesting work again done here at Utah, which goes like this: evolving Mach 3 microkernel to a migrating thread model. So done by 2 people at the University of Utah, David Koch and the student Brian Ford. Brian Ford then went to MIT, became a professor. He's now here. Jay passed away, so he was here at Utah as well. So, but kind of they said, okay, remember Mach microkernel. It was sending messages, but they made this observation that really we simply want to invoke functions. And this migrating thread model is the idea for how to implement this on top of macOS. They were arguing that if you have a thread of execution, you somehow just have to change the isolation boundary. And instead of like, okay, the question is like, what is it instead of? But somehow switch it, but it's kind of the same thread. So like, because remember in a CL4, there will be a guy who's like waiting on the endpoint, and this guy who has a send system call, but this is like thread 1, and this is thread 2, and this if only one of them is running at a time. So it's kind of a synchronous communication, meaning that you kind of keep this thread and it runs. It still like introduces a lot of overhead or more overhead than needed. And in this migrating thread model, the idea is just you have to do something on this boundary, and we'll talk a little bit about it. But then it's the same thread of execution. So you don't have to create like enormous amount of threads in the system. It's just one thread goes through the isolation boundaries, right? There is a range of like interesting things here. So for example, what if A equals B, B equals C? The thread enters C, and meanwhile, some other thread which enters B processes it. Then what happens to this guy when it returns? Well, again, we can choose different constructions. In the systems which I've built, we kind of say, look, the guy skips over. First of all, even if C kind of like went through B and went into C, it continues running. So we don't kill it, despite the fact that it might have some state here left, right? We might even dedicate entire B, but on the way back, we will never return into B. We just skip it and we return into A with an error, saying, okay, wow, B returns you an error, and you judge yourself whether it makes sense or not in your system. But at least he was running for a while, maybe sending messages all over the place, acting as a web server. And then like, it depends. Maybe in some systems you want to clean up the entire stack immediately, but maybe in some systems you want to do something else. Like again, up to you to, but it can happen. And despite the fact that this doesn't look this way, it can happen. This case can happen in both systems, message passing systems as well. Just maybe it's a little bit more hidden. But one of you, who's probably not here, wait, who does fuzzing? It was you? Okay. Yeah, so that's your scenario when you have a graph of those, like, dependency graph of objects in ROS, right? And then, you know, it's kind of like you go here, you run, but this one crushed, like that's kind of a simple scenario here. Okay, cool. So back to this. Okay, we also want to structure everything as a migrating thread, hoping that this crossing will take us less time. Okay, so now the question is like, do we have anything in a modern CPU which allows us to build it? Okay, cool. So what I'm teaching right now, question. Uh-huh.
Sure. One does support this kind of like shading, right?
Wasn't that what?
Single shaded, right? One.
Well, maybe in a deployed scenario, first of all, they have a variety of sorts. Maybe they're now considering even multi-threaded versions of it. I'm not following LASM on a daily basis. I can be behind. I know that it's single threaded, yeah.
So they are trying to follow this kind of.
We'll get to WASM or WASM-like system in just in a second. Like I will explain not exactly the WASM, but the main technique behind it. So, okay, so we wrote this paper just actually just literally was published in the summer this year. And we said, okay, we were working on it for a while, but essentially the idea was that like there's a variety of these new architectural primitives like Intel NPK, ARM pointer authentication, ARM memory tagging extensions like sharing capabilities. It's all nice, we're happy, but we're not sure that people, the hardware architects, really do it right. And we did like in-depth, in our opinion, study, which tries to say, okay, like, is it really done right? The answer, again, the spoiler note, it's not done right, but hopefully we can fix it by observing the lessons from this paper. But essentially, if you wanna, I promised to sign it, so let's assume it's a time to read it today and tomorrow and Wednesday. But that's essentially where this material is coming from. So before we even start and on hardware isolation mechanisms, I will ask you a question. Do you even need any hardware support to make sure that you can enforce isolation or not? It's kind of back to WASM. So what are your thoughts on that? Yes, no. Yes. When people say yes, so what is it you really need? Like my goal is to build my wonderful story. One isolated boundary where we invoke a function f. And in such a manner, let me just explain what I mean by isolation. That if there is a safety bug, because we will step back for a second. And someone like loaded some value in this EAX register in such a manner that it points back here, for example, cannot cross this boundary and is stopped right here. Makes sense? That's kind of isolation. That's kind of an address space or a segment, right? You need hardware support for that. Okay, and how can you build it without hardware? Jerry knows the answer, I see, since he's the author of the paper. You're not on this one? Man, you missed it by like a couple of months, maybe. Zefang is on Zoom. Zandong never shows up. Terz was an intern from India. He said, okay, you guys suck big time. Like, I'm not going to work on this project anymore. Still. Hold on. Let's like optimizations aside, what's the high level idea here? If you have a compiler, right? You can say, look, what if I put a check here? If EAX value is in bounds, inbound. I don't know how to say it. Inbound. Wait, that was EAX. Oh, like, let's say if not, panic. Right? Panic is just a software function which will trigger an exception. So if in front of every instruction, which is a move, for example, which accesses memory, you implement a software check, then you can check for whether EAX is in this boundary, right? Agree? At a high level, idea is very, very simple. And this idea is called software fault isolation. You typically can see it as an SFI. I mean, it's not new. It was developed, let's say, 20, 30 years ago. Of course, you may want to ask a couple of questions here. First of all, what about indirect jump instruction? Jumps come kind of through EAX, right? What if the attacker somehow manipulates this EAX and jumps right past this check? Well, to make sure that we understand, let's assume this is EBX, so it patches both AX and EBX, jumps past the check, so obviously we'll overwrite the memory, right? So how can we do? What can we do for this? Do a check on a jump. There are multiple ways to do it. One way, and this is what's done in VASM. It's never like this. It's more like you have a table of allowed targets. Because VASM is like, higher level specification. It will be a function foo, bar. And really what happens here, you always jump through this table. And EBX is just an index in this table, right? Which called this flavor of technique is called control flow integrity, CFI, which means that you take a program and you keep a track of all allowable transitions. And this is called forward edge of the indirect jump. So for example, it can be a jump or a call. In case of a call, the return address A is saved on a stack. And remember, if attacker somehow overwrites A on the stack, attacker can again return maybe here, right? Agree with this? So you also have to protect the stack. There are techniques to do this. One is called shadow stack. Remember, I talked about it. It's just a separate region of memory, which is sitting in such a manner that none of those instructions or none of the instructions push on the real stack can reach this stack. So this stack kind of sits outside of this address space. And so if you enforce the checks, the attacker cannot override the shadow stack. Agree? And in control flow enforcement, you kind of got it, right? So you can say, look, what if my program uses some assembly, obscure assembly, which a sane compiler cannot enforce control flow? Well, then it doesn't pass a check and you cannot SFI it. But even in most sanely constructed C programs, you can construct allowable. You can figure out allowable targets and implement this control flow enforcement technique, right? Agree with this? So this is pretty much VASM. Great. That's actually my next sentence. But let's get to it in a second. Kind of high-level idea of VASM. VASM has a high-level language specification, and by virtue, whoever designed it, some consortium of people who probably were good in programming languages, said that it will be actually a stack machine. Stack machines, do you remember what stack machines are? Me neither, but the idea is that you encode computation kind of ROP style on a stack, right? So, but in the end, you always compile the stack machine in a imperative program. You can do it, right? And it's faster on the hardware which we're on. So in the end, VASM, when you take, if you take something from C or /Rust, you have a compiler which compiles into some intermediate representation, like which is WASM, and then WASM compilers compile code into something like this, like literally regular assembly stuff with a table which captures allowable control flow, some kind of a settle stack, and those checks, right? And now Jared asks a very kind of sound question. So this check cannot be fast for real, right? What's the intuition here? So if you took Rajiv's class or anyone who teaches architecture, you kind of know that memory access instructions are frequent. How frequent they are? All the time. In my code, all the time. So like how many? Like 10%, 20, how many? On average on stack, let's say. Like Rajiv always uses stack, right? Or like you all guys use stack, some version of stack. So it's nice to kind of, what's your intuition if I ask you a question? No, like. What? Not 40 to 50, but roughly 20%. If every fifth instruction is a memory access instruction, so load or store. On Intel, it's a move, right? So it's like, okay, so if you add, the question is how fast is this check? If you really put an if statement there, then you kind of screw it. It's like X times slower because this check, a branch, CPUs just simply cannot figure it out, like cannot make it fast. So it's out. The question is like, can you make this check to be fast? This is where you, as a systems/architect, like you have to understand architecture quite well. You have to understand what is fast and what is slow. And the first SFI systems were doing something like this, and they were hell slow. But if you carefully stir this check, you will come up with a technique for how to make it fast. So how? Well, speculate.
And then you check.
Wow, it's hard to encode it. The CPUs do whatever they want, right? And they probably speculate underneath. But how to rewrite this check in such a manner that it's fast? You know? Correct. So, and that's essentially the insight. Like, instead of doing this verbose check, introduce some kind of a masking operation. And this mask will somehow enforce that the EAX is in bounds. You can also choose the bounds with some kind of a nice bit granularity, like let's say 4 gigabytes. And then, you just simply like saying that, there might be your current 4 gigabyte chunk, which you will take another register, let's say ECX will contain this number, which just says, okay, you're in chunk number something. So the upper bits will encode the number of the chunk, and the lower bits, or the bits of the EAX register, have to be just essentially zeroed out. And so this portion of EAX is within the chunk, right? Kind of. And plus there are some like additional nonsensical problems with x86, because you can encode the address as EAX plus EBX, meaning that these two can jump out of the chunk, because even if we mask each of them separately, they can overflow, right? And so for that, they actually, instead of doing a 4 gigabyte chunk, they also do a gap. And even if you overflow, you will still land on a gap and get an exception here, right? But that's a detail. So I'll show you how you do this mask, right? And in order, like surprisingly, this control flow enforcement is not very expensive. I'll show in a second. So, but those things are still like masking is the major order. Okay, let's take a look at how we do it. So I think the first paper which did it kind of fast was this one. I don't know if you heard this Google NAC, right? Like if Chrome is Chrome, then this one was called NACL. it was a sandbox for untrusted x86 binaries, meaning when I was a student, that was the first way when you can take a Quake game, or I don't know if you play Quake, back then Quake was the popular game, compile it and run it inside the web browser with almost the native speed, because that thing was actually like it was compiling the untrusted assembly code in with those checks and was executing them inside the browser. It was kind of like, wow, cool. Like before that, we were not able to do it. They were like, they suggest a couple of interesting tricks. Majority like comes to the mask. NACL also uses this interesting construction where they say, instead of enforcing control flow through it, anything like this, they say, well, we'll introduce code bundles. And you can choose the size of a bundle, but let's say 32 bytes. Right? And if you have a jump, instead of enforcing control flow on this EAX, they just enforce the property. You can jump anywhere in your code, but you will always land at the beginning of the bundle. What's the power of this? The power is that the check is always at the beginning or like inside the bundle. So you cannot jump in between the check. So the check and the access like move will never cross the bundle boundary, which means that it was like marginally faster, essentially, instead of and sometimes it's actually, they really took like, instead of taking the C code, they took, I think they were taking, I wouldn't even say either some assemblers or even like object code, and then just enforcing the checks, overriding the boundary, the binary. At this point, like reconstructing control flow would be hard, but and bundling the code and making sure, like, and how you bundle, you just mask. You say, look, the lowest bits are zeros. Like how many bits you need here that forces the jump to be at the beginning of the bundle. And in order to obviously avoid jumping outside of the compartment, you also mask, like do this frequently with a 4 GB chunk, for example, right? Agree? And that was the first implementation which was blazingly fast. So it was like within like on, okay, we will see in a second, but it was like within low percents, like 5, 10, on some like outliers, it takes you longer, but Quake was running like almost native. You got the point. So this is software fault isolation. No hardware at all, just existing hardware. You just use it wisely. Agree? That's a powerful technique because, as you can see in a second, it kind of majority of existing isolation mechanisms require some kind of support from this SFI-like pass. You will do some kind of a masking. Maybe it will not be masking of the bits, but you will be doing something in a second. Okay, so that's my kind of like short primer. NACL, this is how it's written, and WASM doesn't do bundling because the control flow is well defined in WASM. But essentially, if you have a register like RIX, lower bits are within the 4 GB range. You can do instruction move EAX, which is kind of funny. Like it just remove the upper bits. That's how x86 works. You know, there was something, but you take 32-bit version of it to register, you just leave it with zeros. Not too bad. But there are other ways to do those masks. And then, you know, if you have another register like R15, where you say, look, that's my current segment number or location of the segment. So then you do something like RAX plus R15. So kind of doing this trick and really generating the address within the address range, right? And loading something into the register, right? So, and it can look something like this from our implementation, probably, which we built like for this paper, just to do performance measurements. So R15 contains the segment, like essentially the name of your region, and you lower, like you mask the lowest bits, and then this is the syntax in Intel assembly, which is like R15 plus RIX something, right? Okay, cool. So one observation obviously that we do reserve one register. So which means that nowhere in the code this register is used, right? And we do this instrumentation at the level of the compiler. So we take a C code, for example, we have an LLVM instrumentation path, which just essentially rewrites those things, adds those checks into the binary. And that's like, again, pretty common. On ARM, this check is slightly easier because ARM has like a specific instruction, BFI. I forgot exactly what it stands for, but it's some kind of a bit mask operation on these two registers. You can say, okay, which bits you take from where, and it generates you an address, right? But conceptually, it's kind of similar, right? Okay, now, okay, imagine we have it, right? The question is, what will be the overhead of this, right? So that's the plot which we generated. So we have a combination of benchmarks from SPEC 2006 and 2017. The reason for the mix is that not all of them compile easily. So probably with a little bit of work you can, but not everything compiles. And okay, it's normalized to C. And if you just simply take knuckle, as I said, like this is 1, it's normalized. It's almost there. So it's like low percentages for many benchmarks. Sometimes it jumps. So which one as J Ang, I don't know what it is, but like sometimes it gets expensive, right? So not fun. So, but not too bad. And we will take a look at what really like, okay, let me maybe scroll a little. So we say, okay, what is really the reason for those overheads? Like we know what roughly is happening. So we enforce a mask, we enforce control flow, we reserve a register. If I ask you a question, so, and we've seen some rough distribution of the overhead, and I actually have numbers for ARM as well. So if you do spec on ARM, it will be roughly about the same. Or was it showing this one to begin with? I forgot already. Yeah, and I have x86 as well somewhere. Probably this one or something. Oh, it's performance breakdown. This is what I'm trying to ask. Okay, cool. So let's think for a second. So where does the overhead come from? What's the most expensive part of this instrumentation? There are not that many: control flow, masking, reserving a register. So let's say 3. Which one is the most expensive, you think? I agree with you, masking. So, but we wanted to know, right? Since we were working on this paper, we said, okay, we're going to figure it out. So what we did is that we built this SFI scheme and we started applying those techniques incrementally. So we first say, okay, let's just reserve one register. How much performance we're going to lose? And those are the like percent of the performance, right? Or normalize to see how many percent. So like low percents, sometimes like maybe close to 2, but not often. So losing one register is not a problem apparently. That's fine. So the second is like protecting the control flow. So effectively the forward and return edge masking. So it's kind of a shadow stack technique plus going through some kind of a table. Again, takes almost nothing. So here it really like maybe hits you with 2%, but not really much, right? And of course, if you start, okay, but what is the masking technique? Yeah, masking, even just introducing this math, sometimes takes you 20% of performance. Sometimes it takes almost nothing, right? Some kind of video encoding here. They don't have enough memory access, is sort of like CPU bound, but you may like visit enough 20%. I told you, like, okay, Quake was running. Currently, it was close to 20% forward. But so cool. We know this, right? So masking, this one instruction which does the mask, despite the fact that you guys try to speculate like crazy, it's probably a dependent instruction and you cannot execute this one. And since you cannot execute this one, you don't have the result. You can speculate a little bit past this instruction but not much, right? So everything else is kind of like whatever, yeah, almost negligible, but introducing this mask takes a hit, right? So that's why SFI is not like wildly popular, despite that WASM is still deployed quite, as I was saying. So there is a list of companies which will hardly fit on the screen, which now deploy WASM in production. The first one, I think, the first pioneer was really Fastly. I think Fastly was this content distribution network provider, which deploys some code on the edge of the network. But now, like multiple things. But now people are trying to figure out how to make it faster. So in this work, our research was essentially, can we figure out whether it can be done fast? Okay, so what we're doing now is that we start looking at existing hardware mechanisms. And they're a little bit involved, but let's take a look. So the first one, which I will talk about, is called Intel MPK. Those mechanisms, they kind of like, when you look at them, you always have this feeling that they are somewhat under-designed. None of them is like complete. You always need something else. And partially, the reason is probably no one really knew what needs to be done. But second, like those mechanisms also were designed not strictly for isolation, but mostly for the purpose of kind of catching bugs early. So if you have an unsafe bug in your code, it's not about stopping an attacker, but rather like kind of triggering an exception early, kind of like doing a very fast sanitizer in your program, right? Which is also kind of like, you would say, well, is it really worth spending so much effort in it? But the first one is Intel MPK. And in fact, Intel MPK almost can be used for isolation. The idea is the following in Intel MPK. You have a page here. I'm showing it as just one, let's say last week, but there was a whole hierarchy, right? The whole tree. They say, okay, there are some unused bits in the page table, specifically 4 bits. Let's use those bits to encode the tag, like from 0 to 15. Tag number 0 is special. It's only privileged. So if this page is mapped with 0, then it's backward compatible. The checks go away, right? However, if it's non-zero, like 1, for example, we can introduce additional register on a CPU, which is called PKRU. Protection key register for user left. Meaning that it holds a combination of, like it works as 2 pairs. It's 2 bits are controlling whether for the key number 4, whether it's readable or readable and writable. And you can have multiple of those accessible to you at any moment, right? So for example, currently on this diagram, let's imagine for a second, so 0 is disabled, 4 is allowed, read and write. And maybe if I put those ones here, then 31 or then tag 15 will also be accessible. All the pages which have 15 and 1 will be accessible to the current code, right? Agreed? So kind of makes sense. So how will you design isolation in this scenario? What would you do? Like again, remember, our goal is to build this. A, B, how to isolate? That's a tricky question. Exam worthy. Too bad we don't have exams. Let me make a drawing. You have a page table. Here, for every page which you map, you can assign a tag. And you have a current value on the CPU of this register, PKRU, which says which of those tags are allowed. Oh, who is our hero? Just like what? All the pages of A become 1, all the pages of B become, let's say 2, for example, right? At this point, if you have a move instruction which tries to access, wait, that's my EX, tries to access the page of B, since A is running, let's imagine A is running currently. So 1 is allowed, this is 1. But B is 2, 2 is not allowed, right? So which means that this triggers an exception, right? Agree with this? That's isolation? Well, that's not bad, right? There is a couple of quirks here. How do you jump between them? Let's start this way. Maybe it's not the best way to explain, but that's a good way to explain. If you want to call function fn here, or f, how will you jump? Which there is a write pcarry instruction which updates the tag. You can switch it maybe from 1 to 0, right? Which means that the next instruction will be executed with stack 2 and invoke a call of f, for example, right? Agree? And on the way back, you can say, look, write pkru back from 2 to 1. Good? Agree with this? Well, almost. What kind of attacks can happen here? Let's think for a sec. I'll spend just once, and then we'll just make sure that we have this conversation. We understand that it's not as easy. It wasn't probably easy for Intel designers as well. Like, but at a high level, this jumps, like I will replace from A to B, and this one jumps back B to A, and this one executes function F running on B, right? Because here you have what can go wrong? Well, let's start easy, because in practice it kind of gets gets large, and it is. Okay, so first of all, remember we're running. It's a thread of execution, right? So we need to figure out what to do with the stack, right? So first of all, it intuitively feels that if we have something on a stack, it has to be protected from B, because if this function f is a buffer overflow, then it will smash our stack. It might even return somewhere like in the middle of A, and then I don't know what happens, but we can think of it as well. But intuitively, first of all, it has to make sure that this stack is protected, right? So in all of these solutions, when you jump between them, when you have some kind of an endpoint, first of all, the first observation that it's a user level instruction, right? pkru. So it doesn't jump into the kernel, which is great. It's called exitless. It can take up to like 20 cycles. It probably flushes the pipeline. People were talking about it. So it sometimes may take even more than 20, maybe it goes higher. But in many cases, it's very, very fast, like roughly, right? But you really have to do something with the stack. So which means that when you enter this subsystem B, you're kind of executing inside, maybe you don't jump to F directly, but jump to some kind of entry point. Let me just write the entry point label. And this entry point label has to, like, it runs kind of without a stack. Meaning because like you don't trust the stack, maybe the stack pointer SP, like another attacker sets it to point nowhere. And then the moment you execute a push or a pull, you immediately crash, and that's the way to launch a denial of service attack, right? So obviously it's not good. So what you do here, you first like you execute a sequence which picks the stack, picks a new stack. And how can we do it? How can we pick a new stack? What? What does it mean to pick a stack? Well, there are multiple ways to do it, but let's just spend like 2 minutes thinking about it so you at least remember. Because if I explain it, I just afraid that it's not gonna stay in your head. Like you really need a stack. Where can it come from? We don't trust the A because A can pass by the fact A can pass any garbage in any register. So we don't trust what's coming in registers either. Right? Because A might be malicious, tries to exploit B. They don't trust each other in a general scenario. We do what? Kernel. We can get it from a kernel. How? Well, doing a system call is not a good idea because it will cost us 100 cycles right away. And those instructions are so fast that we want to make sure that we don't spend like 100 cycles. Well, why not to have a global variable in B, which holds like a list of stacks? Yeah, it's a variable in our memory. So supposedly A cannot attack, right? And then it has like a list of stacks. And the code here just picks the one from the front of the list. Why not? And sets ESP register to point to this stack. We can even check, like, does it make sense? Right? Since we cannot trust the registers. Registers are garbage. We have to only trust our memory, but we can have a global variable from which points to the list of stacks. If we run out of stacks, we go to the operating systems or to the trusted runtime, says, okay, allocate us more stacks. And then you have more on the list. But typically you just pick a stack from a list, right? Agree with this? This is clear? Makes sense? If we, like, there is one nuance here. So because what happens if a second thread invokes maybe two threads simultaneously try to invoke a function inside B? Maybe it's the same function, maybe it's different, but they both try to compete for the stacks, right? Because we want to build this environment to be multi-threaded. So this list has to be protected by a lock. It can be done with a spin lock. It's not ideal probably, but you can easily write not a generic list, but implementation of a, what is called a queue, like first in, last out. What is it? FIFO? FIFO, first in, first out. Yeah, but essentially, I think it's more like a stack, right? So then it's easy because it's one compare and swap here. And then it's again, if it's not under contention, if it's under contention, then go don't remember this. You remember those things, right? Michael Scott list, MCS list, right? So, but if you're not under strong contention, a single compare and swap does. But we pick a stack, right? We got it? So that's one part which we wanna, and after that, you probably can already like run fn because you have a stack, everything is fine. How will we pass arguments? Or how will we pass anything from A to B? Remember my exchange heap, which I mentioned. Or let's say for the sake of it, let's pass a number. How will we pass a number? Like a scalar value between A to B. Like imagine a function f takes an integer argument. How will we pass this A? that requires some kind of a trusted computing base, which has access to both stacks. It's doable, and we also did it. But it means that you first have to jump to the TCP and then jump from TCP into the B, which probably means that you have to execute a couple of, like at least 2 more write PKRU instructions on every invocation. But it's not a bad idea, so it's doable this way. However, let's be simple for a second. We say, look, we pass it in register. We will come up with an ABI. And register EIX, for example, will contain the first argument, right? For scalar values, it's okay. So F, the callee, has to check that this argument makes sense. So for example, if the caller cannot pass a 0, then you have to check for a non-zero value. But whatever the semantic check is needed will be done here. I wanted to stop for a second. What happens with other registers? Like imagine we say EAX is the one register, EBX is the second argument, and after that we don't have ABI. We allow only to pass 2, just for the sake of example, allow to pass 2 scalar values. What do we do with other registers? ECX and so on. My point is that since we don't trust B, we cannot leave them in registers, right? If you trust B, B will implement a proper calling convention. It will save and restore the registers. But maybe before calling Fn, our own register ECX contained a pointer to an object on our heap. And if we allow B control this register, then this can be pointing again to null, and it will crush us, right? So before calling B, we have to actually save all the registers on a stack, right? So like right here, because before doing this write PKRU, you have to save all registers, right? Because besides maybe EAX and EBX, because those are passed. And here we have to restore them. You agree with this? That makes sense, just because we don't trust the callee, right? Callee can overwrite any registers. So we will save them. We can save them on this stack, on our stack, right? So we don't need anything special. Just let's put them on a stack, right? There is an additional wrinkle. Do you guys know what those extended registers are? What are those? You must know what extended registers are.
Stand-up,
Extended.
extended.
Uh-huh. I'll write the first letter of them. Some subset of those extended registers. ADX. So like extended registers are like used to be floating point registers, MMX, then Intel kept trolling. Now we have ADX, those long like 512-bit registers, right, for vectorized operations. Well, it turns out that modern compilers aggressively use those registers. Like if you disassemble LLVM code, you will see that, suddenly like you wrote an integer program and suddenly, like you see some MMX registers all over the place. Compilers figured out that, like sometimes it's faster, like nothing is like vectorized, but somehow they're used. Like a good example, like memcpy, the memory copy instructions, functions, those are like super optimized with those registers. But even some completely non-vector code, which you wrote yourself in Rust, which is I'm saying Rust, just because I've seen it in LLVM used by Rust compiler, but I'm pretty sure C++ and C will be using the same. They use those registers. And again, we don't trust the calling, so we have to do what with those registers? Yeah, we have to save and restore them, right? So it turns out that in all this kind of like, remember, we remember context switch from x86, we never talked about extended registers. But it turns out, because x86 doesn't support floating point registers, like nothing like that. But you actually have to save those ADX. I will put ADX if it's easier to remember, but all of those registers are just generically called extended registers, and restore them as well. Got it? They can be also saved. There is a specific instruction. It saves them on the stack as well. Okay, cool. So this is nice. So we at least protect A from B. It seems like, right? This write PKRU instruction on Intel. I think it uses a register as an example, as an argument.
Who's doing all this?
Run your compiler, yeah, I mean,
Maybe yet this.
yeah, we'll get like how to pass a pointer, something behind a pointer. I'll get to it in a second, right? Just one more attack, and then we'll go there. Just give me a sec. So I'll finish it in like 2 minutes. In practice, this is how this instruction is written. It immediately becomes kind of cumbersome. You say, look, guys, what if an attacker loads EAX with something bogus and jumps right here? Because you can say, look, guys, maybe there is some kind of a check if you want to implement the check here, but really the instruction is dynamic. So it depends on the register. If an attacker writes kind of 5 here, then an additional wrinkle here that Intel doesn't check PKRU for control for flow transitions, only for loads and stores. So you can jump anywhere in the address space. In fact, if you're clever enough, you can even find something like write PKRU instruction somewhere here, which uses some value. Maybe it jumps to like C or somewhere, but attacker from A can jump directly to this instruction because this is allowed. Intel just simply decided not to check this, which is a little obscure or awkward, right? But maybe there was a good reason. Which means that if you just take an unsafe binary, attackers can manipulate, like jump in the middle of somewhere, like jump right here, having EAX5, call with this function fn, but instead of executing inside B, it will be executing maybe inside C, or maybe, like, God forbid, you can even write 0 here, like this super powerful tag, right? That's even worse. So how will we deal with this attack? I'm not sure Intel knew either. Why are you taking it personal? Does it matter whether I like MTK?
He's very good, very.
You will see other mechanisms there. They're equally weird. It's not about me. It's about you. Like you're learning. You're the next generation. But you see that it's a problem, right? Do you think I like it?
No.
I love it. Gives me money. So either you have to enforce control flow, like CFI style, make sure that attackers cannot like jump in the middle of something. An additional wrinkle here that, like, remember on Intel, if you jump in the middle of a move instruction, you can start executing it from the second byte or something. Maybe it turns out into write PKRU, right? Or write PKRU, right? Remember it was a couple of weeks, last week, right? When I said on Intel, remember those ROP gadgets, remote return oriented programming. You jump, move starts here, first byte. You don't start executing move from first byte, execute it from the second byte. And then suddenly this sequence of bits is interpreted by the CPU during the decode stage as the write PKRU instruction. Like crazy, right? So and maybe it writes 0 here or something, right? And so people came up with techniques for how to protect those attacks. Like I'm just like, again, mine is more of a kind of like high level overview just to show the craziness of this. But really, if you want to jump in the middle of instruction, which turns into write PKRU, you really either have to enforce control flow, which is not always, as I was saying, it's not always feasible for binaries which use assembly code. Like then, there's a lot of indirect jumps, and the register can jump anywhere. Static analysis sometimes fails because it doesn't correctly resolve the aliases, and you don't have this table. In case of WASM, you do. But so people came up with this trick, Jared. You will there are two tricks. First of all, the first trick is a linear scan of the program binary. And if any of those bytes gets interpreted as right PKRU, a team from Germany, Peter Durschel, came up with a technique to say, look, I will replace this instruction with an equivalent instruction. It will also be moved, but in such a manner that this equivalent instruction will use some kind of a different encoding scheme, and it doesn't turn into right PKRU. So all over the code, you just if you see that something can turn into right PKRU, you do a transformation on a binary which does equivalent thing in assembly code, but it doesn't turn into right PKRU. To defend against just rogue right PKRU instructions. It's called airing. Right? That's one. But the second one is even crazier. They say the second team from Rochester, University of Rochester, and it's all published. I'm not making it up. This is a powerful paper, but the second one, Fodor. I think it's called Fodor. They say, look, if we see something that can turn into right PKRU, we will protect against it. How? We'll use a hardware breakpoint. Intel has a limited number of hardware breakpoints. I think it's literally maybe 4, which means that they can protect 4 instances. But essentially, if the attacker starts executing this sequence, you get a hardware breakpoint. And then the runtime thinks, okay, it's kind of like you're under attack or something. Yeah, that's kind of cute. And when you run out of those right PKRU instructions, then you write protect or execute protect the page or something like that. So Fodor airing. I'm just saying that, okay, so it's not easy to make this right? Although it seems like, okay, cool, what can go wrong? Everything is super duper cute, right? Okay, I'm 5 minutes over. So I'll come back on, what is it, Monday? Right? No, Wednesday. Yeah, I'll come back on Wednesday and we'll start from passing something through by reference, how to do it, right? But okay, you kind of get this. So at this point, maybe start reading the paper. And if you care to read about airing, there will be a link to airing and Fodor probably as well. So it's kind of interesting. So, but it will take me some time. I'll finish a couple of those mechanisms. They're kind of interesting. Okay, thank you. So I'll stop here.